Hey everybody, we're going to do notes on mixtures and a little bit of an intro to separating mixtures. So go ahead and title your page mixtures. I'm going to walk you through these notes and kind of do some explanations and descriptions. Hopefully it's large enough for you to read it. Remember, these are always in your course resources as well. So this is sort of a review. We're starting our second unit now. This unit is on mixtures. Our first unit, we talked about mixtures for a brief minute. And then we focused on the pure substances side of our matter flow chart. Now we're going to go into the mixture side of the matter flow chart and work with those. So mixtures are two or more pure substances physically combined. So we take two or more elements or compounds, or elements and compounds, and we basically put them together physically. They're just in the same container. That would be a physical combination. Put them together in the same container. And we're going to talk about physical combination next. So what does physical combination mean? It means no chemical bonds are formed. No chemical bonds are formed. And you guys can pause this video as much as you need to get this stuff down. And each substance retains its own properties. So you still have the two substances you started with. They're just together now. When you put frosting on a cake, you still have the cake, you still have the frosting, they're physically mixed, but they retain their own identities. But frosting and cake are both mixtures themselves. If you think about frosting, it kind of depends, but a really basic frosting might be just butter and powdered sugar. Those two things mixed together, the frosting still has properties of both because both of the substances are still there. It has not created a new substance. This example is a little bit easier to think about, I think. Salt and sand mixed together is a mixture. So I take some salt, put it in a container, take some sand, put it in a container, stir it up, and you've got a mixture. Now, physically combined, no chemical bonds have formed. We haven't made new things. The salt and the sand still exist. If you look closely, you could pick out a grain of sand or a crystal of salt. If you put a scoop of that mixture in your mouth, I mean, just imagine that for a second, a scoop of salt and sand in your mouth, okay, that mixture, it would still taste salty, but it would feel really gritty. So you still have the salt properties and the sand properties in there. They keep their properties. That makes it a mixture, okay? Now, we've been talking about this a little bit. If we think about salt, I'm just going to type the chemical formula for salt in here. You don't necessarily need to go back and add that, but NaCl, okay? Salt is sodium chloride. Our table salt is sodium chloride. Remember, sodium is an element, and if you put it in water, it explodes. And chlorine is an element that if you breathe it in, it's a green gas, it's super sharp odor, and it will just destroy your lungs, okay? Those two elements together make salt, but it's not a mixture. Otherwise, when we put salt in our mouth, the sodium would explode and the chlorine would start eating through our lungs, right? It's not a mixture. When you form chemical bonds between these two elements, that makes it a substance that has totally different properties. It's a white solid, it dissolves in water, and we have to eat it in order to survive, right? So that's the difference between a compound, which has two elements bonded to each other, and a mixture. Salt and sand, they keep their identities. We still taste the salt, we still feel the sand. So physically mixed, not chemically combined, okay? If you need to pause the video, please pause it. But I'm going to scroll down and move on to the next piece. All right, another piece about mixtures, the ratio of the components can change. You could add or remove some salt and still have a salt and sand mixture, okay? So it is all about, you can change that ratio. Whereas again, if I typed NaCl, you have to have one sodium for every one chloride in that compound. It has to be a 1-to-1 ratio. I can't add more sodium or more chloride and not add the other, or it wouldn't be salt anymore. Whereas salt and sand, if I add more of one or the other, you still have a mixture of salt and sand. It's just a different type of that mixture. Now we have two types of mixtures, which we've learned about already. We have homogeneous, which is the same throughout. You cannot tell it's a mixture by looking at it. It's uniform is another way to say same throughout. Okay, homo means same, same throughout. Heterogeneous is different throughout. You can see the different parts of the mixture. So when you mix sand and salt, if you were to look at that one, you could see the crystals of sand, you could see the grains of salt, crystals of salt, grains of sand. Anyway, you can see them both. Because you can differentiate just by looking at it, that makes that a heterogeneous mixture. Okay, now we're going to go through solid, liquid, and gas examples of each of these mixtures. So pause if you need to, and then we're going to make a table, homogeneous in one column, heterogeneous in the other, and then go through solids, liquids, and gases. So here is that table. Remember, homogeneous mixture is the same throughout. An example of a solid homogeneous mixture is steel. Whoops. Sorry, guys, having technical difficulties. Okay, steel, that is solid and homogeneous. When you look at steel, you can't really tell that it's a mixture, but steel is not one element. It's mostly iron, but it's going to have other elements in it, and it depends on the type of steel. We've got steel made with just iron and carbon. You've got iron, carbon, chromium, titanium. Lots of different metals can be mixed in with the iron and the carbon in order to make different kinds of steel, surgical steel, stainless steel, all of those. But they mix perfectly uniform, so that makes it homogeneous. Heterogeneous solid mixture would be like granite, the rocks at Meadville. If you look at them, they have different crystals of different components to the granite, or even just sand. You can get some pretty pure sand on certain beaches around the world, or you can order sand that's very pure looking, pretty pure. It's going to be mostly silicon dioxide. But if you just go outside and pick up some sand off of the ground, you're going to have lots of variation in there, and that's going to be heterogeneous. So that's what I was thinking of when I was looking at these. So those are two heterogeneous solid examples. Homogeneous liquid. Okay, I put a few in here. Milk is homogeneous. If you've ever noticed on a milk label, it says homogenized, which means they have forced it to be homogeneous, because milk straight from the cow won't be homogeneous. If you let it sit, it separates, cream on the top, the less fatty parts on the bottom, okay? But homogenized milk has been forced to be homogeneous. So the milk we buy at the store is homogeneous, unless it's rotten, and then that pushes it over to that heterogeneous side. Diesel is a blend of a bunch of different hydrocarbons. We're going to learn about that when we get to our organic chemistry unit. And Kool-Aid, when you dissolve that Kool-Aid sugar or Gatorade powder into water and you make that perfectly uniform solution, it's the same color throughout, there's no crystals on the bottom because you didn't over add your sugar, that's going to be a homogeneous liquid mixture. Okay, so dissolved things also become homogeneous liquid mixtures. Okay, heterogeneous, I just chose two salad dressings here. So ranch dressing, you can see it's white, but then it has the little specks of like spices in it. So that would be heterogeneous. You can see the difference there. A vinaigrette, usually, the oil and the vinegar at the very minimum. And then if it has spices or garlic or anything in there too, you can see those floaties in the dressing. And that's a heterogeneous liquid mixture. Okay. Really, oil and vinegar by themselves would be a heterogeneous mixture, because the oil separates from the vinegar. So you have that two layers. Okay, homogeneous gas mixture would be air, clean air. When you are in a room in our buildings, we have very clean air. It's very equally distributed, nitrogen, oxygen, carbon dioxide. There's some water vapor in there. All of those gases very evenly distributed, so that makes that homogeneous mixture. And then heterogeneous gas mixture would be like smoky air. Okay, if I light a match and blow it out, you can see the smoke coming up. That is a heterogeneous piece to the air because it is not uniform anymore. Okay, cloudy air, we'll look outside, we see the clouds up in the sky. That is technically still gas. It's water vapor collecting together up there, but it is still gas form because it's vapor, and that makes that heterogeneous because we can see that difference. Or smog over a city. When you're driving to Denver, especially in the wintertime, you might notice that there's a brown cloud over the city of Denver, and that's a heterogeneous. If you take that huge sample of the air over Denver, you're going to see that that's heterogeneous. So it kind of depends on the size of your sample. Clean air would be like small sample sizes. When you get into smoggy air, cloudy air, smoky air, you're looking at a bigger sample size usually in order to see the differences within that mixture. Okay, now we're going to talk about separating mixtures for a few minutes here. Pause the video again if you need to, but I'm just going to go through this. So separating mixtures. To separate a mixture, we use physical properties and physical changes. I'm just going to add the word physical here just to make sure that you don't lose track of that when we're talking about this, okay? Physical properties and physical changes. Now, what does that mean? Well, we're going to talk about them. Physical properties. Again, if I'm going too fast, make sure you pause it. Something you can observe or measure without changing the substance. And then a whole bunch of examples here. Color. If I look at what color this marker is, I'm not changing the marker into something new. So color is a physical property. I can tell what color it is without changing it. Shape, density. When you measure the mass and the volume of your object and figure out its density, you don't actually have to change what the object is made out of. So mass, volume, density. Magnetism, okay? If I stick a magnet to a whiteboard or a refrigerator and then I pull it off, it's still the same thing. Nothing changed about the refrigerator, nothing changed about the magnet. That's a physical property, whether it's magnetic or not. If I test the magnetism of this marker, I stick it on the refrigerator and drop it, and it's going to fall because it's not magnetic, okay? That is also still physical property, not magnetic, right? I didn't change it when I tested it. Boiling point, when you boil water, it's still H2O. It's just turning into H2O vapor or gas form of water. Freezing point, same thing. When you freeze water, it's still H2O. It's just becoming ice. Melting point. Solubility. Ooh, this is a good one. Again, if I'm going too fast, slow me down, pause me, whatever you need. Make sure you get this one in your list though. Solubility. Solubility means ability to dissolve in water. So when you dissolve salt in water or sugar in water, that's a physical property. It's still salt. Okay, if you dissolve salt in water, it's still salt. When you drink it, you still taste the salt. It has not changed into something new. It's just mixed. So that's a physical property. Okay. Sugar, same thing. When you dissolve sugar, you can still taste it. So solubility is dissolving in water. That is a physical property. All right, physical changes are very similar to physical properties. Okay, it's a change that affects some properties, but does not change the composition. Okay, so, and these can sometimes go with these. They pair up a little bit, but if I fold something, I fold a piece of paper, or I fold a sheet, I haven't changed what it's made of, so that is a physical property, physical change, excuse me. Crumpling or getting something wet, those are physical changes. Dissolving, so here's one, this one goes with solubility. When I dissolve salt, it is still salt, it is still water. They're just mixed together in a homogeneous way, okay? So dissolving is a physical change. Evaporating, physical change. When I evaporate water, it goes away, but it's not changing into something else. It's changing into water vapor. It's still water, just in a gas form. And that's actually a really cool way to separate salt from water. Just evaporate the water. The salt doesn't evaporate, it stays behind in the container. Same thing with sugar. If you leave like Gatorade out, just a little bit of Gatorade in a cup, leave it out for a couple days, the water will go away and you'll end up with the sugar and the dyes and whatever else, the electrolytes are all going to crystallize out of that mixture. Tearing, cutting, grinding something up, grinding up some peppercorns to make pepper. Filtering, when you filter the coffee grounds out of your coffee, okay, you're allowing some of the dissolved part of the coffee to go through, but you're not actually changing anything into new substances. You just created a solution, a homogeneous mixture of the pieces of coffee that do dissolve with the water. Extracting, sorting, when you sort your dishes at home, that's a physical change, okay? And then these two that start with D, these ones I want you to definitely get because they're very specific examples that we're going to refer back to over and over and over. Distillation. Distillation is removing water from a mixture. Now, if you have heard of this word before, distillation, it's probably in reference to alcohol, because when we distill beverages, we're removing water and that increases the concentration of alcohol. So the still or any still is technically a company that is removing water and creating more concentrated alcoholic beverages. But the word distillation only means removing water from a mixture. So if you leave that Gatorade out to evaporate, the water goes away. Technically, you are distilling your Gatorade and you're just making a concentrated, either syrupy, sugary mixture, or if you let it dry all the way, you're going to end up with those crystallized sugar crystals in there. Okay, that's distillation. All right, decanting. Decanting is removing the top layer of a mixture, removing the top layer of a mixture. So if you are one of those people who likes to take your cupcake and eat the frosting right off the top before you eat the cupcake, technically you're decanting the cupcake. You're decanting the frosting from the cupcake, okay? Or if you eat the whipped cream off of the top of your coffee drink before you drink the coffee drink or the milkshake or whatever you have whipped cream on top of, that's decanting a mixture. For chemistry purposes, sometimes you'll have, again, like an oil and water mixture, and you want to separate that. To pour that water or that oil off the top of the mixture would be decanting. So those kinds of separations where you're taking the top layer of a mixture are called decanting. And these two words are going to come up over and over and over in our labs, our activities, and on your tests when we get to our Unit 2 assessment. Okay, so we've done mixtures, we've done separating mixtures. Again, if you need to see those notes, they are in the course resources. The chromatography notes are going to come later, so we'll do those later. Don't worry about those yet, or you'll be bored when we take those notes. So hopefully you got what you need, and I will see you in class.